again, and we'll meet in 5 minutes for the next lecture. To introduce Ron from Australian National University, and he will tell us about counting, generating functions, and zeta functions.
Thanks, Masood. Good morning, good afternoon, everyone. I'm going to tell you about representation zeta functions. This is a fairly young area of research, but it builds on other things, and it's also connected to many other areas, and I will bring them up as we go on. There will be the worksheet will be on Slack later on today. There are some easy problems, some more difficult problems, challenging problems. It's very important that you try them and attempt them. And keep me posted whether you are, that I'm pitching the right level. So you should be getting things from this course. And so slow me down or push me faster if needed. Really, don't be afraid. So the beginning of this story is, I could say it's an asymptotic, maybe asymptotic or, yeah, let's call it asymptotic group theory. Group or ring theory, where the idea is to take some algebraic object and somehow cook up from this object a sequence of numbers, of natural numbers that depend on the object. And try to see whether you can learn something from what's the relationship between the object and this natural sequence of numbers. And that's what we are going to do, right? It's not so scary. Let me give you 4 examples of things that were done actually for many years. So the first example, suppose that G is a finitely generated group, say generated by a set S, S1, say up to Sm. And here's a sequence of numbers that we can attach to this situation. So An will be An of depending on G and on S. So for every element G in G, we will count the number of elements that can be written with less than n generators. So there exists a sequence Si1 up to Si, say J, with J less or equal from N. If you think about the Kelly graph, this is the distance of your element from the origin. Okay, so and this is called the volume sequence of the group with respect to these generators. And a famous theorem by Gromov, so Gromov, prove that this sequence grows polynomially, or say bounded by a polynomial. This is the volume growth. Volume growth sequence, and An grows polynomially if and only if the group G is virtually nilpotent. So virtually means up to finite index. So G may be not nilpotent, but it contains a finite index subgroup which is nilpotent. So this is an example of an algebraic result that depends on just the growth of the sequence. If things grows polynomially, then the group is virtually nilpotent. Another example, which I will talk about in more details, but I already want to write it here, is that if K over Q is a number field, so that's just a finite extension of Q. And if we take R to be the ring of integers, then let's define the sequence Bn. Bn depends on R, of the number of ideals in R, such that the index of the ideal is n. So in this case, the sequence grows linearly, and this sequence is the basis for analytic number theory, and I will go back to this sequence soon. And the third example, which is what we are going to study in detail, is the following. So we take a group, G is a group, and the numbers that we are going to look at, Rn of G, is going to be the number of irreducible representations of G. So I'm looking at representations of G which are n-dimensional, irreducible, n-dimensional because we already have the n over there, and we cannot count anything in mathematics as objects, right? We can only count things up to isomorphism. So we are going to count isomorphism classes of representations. So these are the numbers. This is the sequence that we'll be focusing most of the time. But I will get to that soon. I want to talk a little bit about generating functions and zeta functions and give you some background, but also I'm going to use this knowledge and transport it to representation zeta functions. So one of the things that is very useful to do is to take the sequence and put it in a generating function. So a generating function and there are two frequently used generating functions. You can take this sequence and you can associate to it a formal power series, which you've seen, I guess, in many areas in mathematics. So that's an element in this case where I'm taking integer coefficients, then that will be in formal power series with one variable and over the integers. So that's one type of generating function, which is very useful. And the other one, which is also used, the starting was in analytic number theory, was to use a Dirichlet generating function. So to look at the sum of the form an n to the minus s and goes from 1 to infinity, that will be a Dirichlet generating function. And here s is a complex variable, but what we need to make sure that our object, that this function is defined, and for that here's an exercise. So an exercise will be to show that if an grows polynomially, so if there's a constant such that this sequence is bounded by a polynomial, then this power series, which I will maybe now give it a name. Okay. At this point, just call it f of s. Then there exists a sigma such that a real number such that this function, so that f of s converges on a half plane with all the elements with real s greater than sigma. And the infimum of all these is called the abscissa of convergence. So the infimum of all those sigmas is called the abscissa of convergence. And that's going to play an important role. So let me maybe call it a definition. Are there any questions so far? Okay. So let's go back now to the sequence Bn that I defined here. And let's take the case where we are with k equals just irrational numbers. So that will be now a small discussion on the Riemann zeta function. I should say maybe the idea of packaging all these numbers in one object is very useful. So you take an infinite amount of information and you put it into one object, this generating function. And it turns out that you can extract very useful information about the sequence from that generating function, either whether it's the Dirichlet series or the ordinary generating function. And here, for example, you can also capitalize on methods from complex analysis. And as you will see, or probably most of you already know, this is extremely useful. So now I'm just taking k over q, but my k is q, and so my ring of integers is z. And so the numbers bn of z, this is the number of ideals in Z, such that the index is n, and there are not too many of them, right? So this is identically 1. The most silliest sequence that one can imagine. But let's see how much information, if you put it in the right way and you look in the right direction, you can see. So the Riemann zeta function is the Dirichlet generating function, which is the sum and goes from 1 to infinity with these ones. So this is just n to the minus s. And one can write it down as an Euler product. There's an Euler product decomposition where you go over all the prime numbers and you look at 1 minus p to the minus s to the minus 1. So this is called Euler product decomposition. And there's if you haven't seen it before, then it's a nice exercise. Prove this. And you might find the fundamental theorem of arithmetic handy here. So hint. Use the fundamental theorem of arithmetic. How many of you have seen this? Okay, great. Now, how much information does this function contain? Well, it contains a lot of information. So if you
Z equals to
Sorry?
top of the string, we have Z equals 1.
I mean, this number.
Repeat the question.
Yeah. So the question is, what do I mean by always one? Yeah. So you take the integers. How many subgroups of index n does it have? So every subgroup of the integer is cyclic, and it's just isomorphic to Z. So there's only one of any given index. But Z is also abelian, so this is also a normal subgroup. But Z is also a ring, so this is also an ideal. So the number of ideals in Z of index n is one. There's only one. So here it is. It never happens like that. Yeah, but here it is. So I is equal to, sorry, I is equal to NZ. That's your I. Yeah, so there's only one. So now if you look at the Riemann zeta function, let's see what we can say about it. So firstly, to begin with, this sum here converges only for real s equal greater than 1, right? So the abscissa here is s equals 1. So without any effort, there's this function defined, there's an analytic function defined on this complex right half plane. But Riemann proved that it has a meromorphic continuation. So in 8-page paper, quite remarkable, he proved that it has meromorphic continuation. Has meromorphic continuation, and in fact, if you just slightly change it by multiplying with a gamma factor, then you see that this zeta function satisfies the functional equation. I mean, this is to begin with. You just observe that this is a convenient factor to add, so that you get a functional equation. So the functional equation looks nice, but you could, of course, bring it back and use zeta of s, and you'll get some functional equation. There is a relation between zeta of s and zeta of 1 minus s, except it will not look as nice if you choose just zeta of s. Okay. So it has a meromorphic continuation to the whole plane, the completed one. So this zeta tilde, and it has a pole at 1, and it has a pole at 0, of course, because of a functional equation, and that's it. Okay. And now, what does this function know about the primes? So so the fact that zeta of 1 is infinite, this is equivalent to the existence of infinitely many primes. Right? Let me just write it down. If you have sigma of 1 over n, if this is equal to product 1 minus p, the minus 1, this is, of course, I should put it. So both sides diverge, but what happens is that we know that this series diverges 1 over n, and therefore there must be infinitely many primes. That's Euler's proof. The fact that zeta of 1 plus it does not vanish on the line, on the imaginary line passing through 1, is equivalent to the prime number theorem. That is, that the number of primes up to x is asymptotically x over log x. So the ratio between these two quantities goes to 1. And that is really equivalent to the non-vanishing of the zeta function on that axis. And if you dig further and you look at the vanishing properties in the critical strip, then the Riemann hypothesis is equivalent to the fact that the only zeros of the zeta of the meromorphic continuation of the zeta function is on the real line passing through. The line passing through half. So there's an enormous amount of information, and you see, I couldn't do that. All this with the sequence. I couldn't do that. It's kind of putting this into the zeta function that brought all these wonderful results into play. And particularly, the function does not exist here. I mean, you begin with the sequence. It just defines something on the right to the number 1, but then you can extract information even places that the function was not defined to begin with. So that is an example of what you can do. I mean, that's the best you can do, actually. I mean, nobody can beat that. It's so much structure in number theory that we are trying to approach or approximate or take ideas, but we will never get to the richness of these zeta functions. But I want to tell you one more thing about these zeta functions, and in fact also on the Dedekind zeta function. So the Dedekind zeta function is the one that you define by taking the b ends for arbitrary ring of integers, and many properties of or a very conceptual approach to these zeta functions was given by Tate. So, and that's what I want to talk about. And for that, I need to introduce the P-adic numbers and talk a little bit about them. Who saw the P-adic numbers here? Who didn't? Okay. I'm going to give you a sketch, and then we'll have many exercises, and then you're most welcome, those who haven't seen it, to ask me questions and fight with problems to get it right. And because I will need them very in various places. So let me talk about the P-adic numbers. And then I will go back to the zeta function and see what can be done with them over there. So maybe before I'm writing anything, the whole idea is to try and have some analysis inside algebra. So the integers, this is a discrete object. It has no other structure except for a ring. And in many situations, if you add topology, for example, suddenly you get some rigidity, or you get some constraints that allow you to say much more things when you have topology. So let me just give you, this is a motivating example. Say, maybe you've seen, I'm sure most of you have seen it. So if I'm asking how many functions from R to R satisfy f of x plus y equals f of x plus f of y. How many additive functions there are from R to R? Well, there are a lot. It's basically you can show that this is any map like that is Q linear. So this is Z linear, but you can show that this is Q linear. So the collection of all these, what it is it's hom Q from R to R. So maybe you need to think a little bit about that, but certainly this is by definition hom Z from R to R, but I'm claiming that this is the same as asking for Q. Now R is infinite dimensional over Q. So this is a huge non-commutative object. But if you look at continuous map, how many of these are continuous? So I'm adding an extra feature and I'm just asking these maps to be continuous. Then it's an exercise, if you haven't seen it, to show that it must be R linear. Because if you know something which is continuous over R, over Q, and you know the values of the function, it immediately tells you what the values are over R. So, and that's just R. So you see there's a big difference there. So that's what happens when you kind of blend algebra and topology. And that's the direction that we are going. And we are going to do this with the P-adic numbers, which I want to define now quickly. So I want to define, so here's the definition. Evaluation on Q, it will be a map from Q to Z union infinity. And the definition is going to be VP of A over B. I will take the maximal P power that I can from A and B. I'll have you say P to the R, A prime over B prime. And now I want A prime and B prime be coprime to P. And I will define this as P to the minus R. Sorry, as that's the next thing that I want to define. Here it will just be R. And now to this evaluation, I want to slightly change the definition and not change, use it to define another function that's going to be a function that goes from Q to the non-negative reals, defined by the absolute value or norm of A over B to be P to the minus the valuation of the number. Don't need it, X and X. So this is a norm or absolute value and indeed you can easily prove that this is a norm, so satisfies the first thing is that the norm of a number is 0, if and only if it's the 0 element. And the second thing is that it is multiplicative. And the third thing is that X plus Y is less or equal to X plus Y. Now, this is the definition of a norm. But if this function satisfies the stronger requirement, that x plus y is less or equal to the maximum of x and y, then this is called an ultranorm. Okay, that's an ultranorm, and we can now define the p-adics, or maybe before that, whenever I have a norm, I can, so given a norm, I can write down a metric, I can define a metric, so d of xy is the norm of x minus y. And you can easily see that given a norm, you get a metric. And now I can define the p-adic numbers. So QP is the completion of Q with respect to the norm, to the p-adic norm. Okay, so for every prime, I have a norm, and therefore I have a metric, and I can complete the rationals with respect to this norm. And inside, so the p-adic integers, so ZP is the completion of Z with respect to the norm. So these sit inside QP. And this is really crucial to what we are going to do. And so I want to talk about it in more details, and I want you to work hard on a few exercises related to this, to get a feeling of how does it look and what can be done with them. So here's your first, that's going to be your first exercise. That's question number 1. So I'm going to put this worksheet on Slack, and I'm going to update it with more and more exercises. And your first exercise is to prove that there are 3 ways to think about the p-adic integers. I'm actually going to do it now. So I'm going to spell out what each of these means. And yeah, let's see how does this look. So the first definition is just completing with respect to the metric. This is something that you're used to if you are using the usual absolute value, because if you are completing, so just recall. So recall that if I complete the rational numbers with respect to the usual absolute value, I get the real numbers. So now here, this is the usual absolute value, which is not an ultra. It's but all these are ultra norms. So for the p-adic norms, it's the stronger one that that you can prove, and this is extremely useful. This is extremely, there's a big difference between being a norm and an ultra norm, and an ultra norm gives you a much better properties. So what are the other 2 alternative definitions? So so now I want to give alternative definitions of ZP. So the first one is well, I gave you the first one. This is the completion. The second one is the following. So 2, let's call it 2. So I'm taking the infinite product of z modulo p to the nz, and goes from 0 to infinity. So this is an infinite product of the finite rings. And inside, I'm looking at the sequences an, such that an plus 1 is congruent to an modulo p to the n. Okay, so these sequences, they are compatible. So if I take an element sequence, there's a relation between the individual elements. Each one should be congruent to the lower one modulo the lower power. Okay, so these are compatible sequences. So that's the second definition. This is a second. You could write it down as a second definition of the P-adic integers. And the third definition is you look at the maps from, you have canonical maps from z modulo pz, and then z modulo p square z, and then z modulo p cubed z, etc. And you look at this diagram, and if you think the inverse limit in the category, you take the inverse limit of that sequence. So the inverse limit has the property, it's the universal object that has maps to all of them, such that all these are commuting arrows. And it's the closest one to the diagram. So for every other element, if I have here some y that maps to all of them, it must factor through the inverse limit. Okay, so that's a third way to think about the P-adic numbers. And all of them are very useful. And your exercise is to show that these are all equivalent definitions and to feel comfortable with them. Okay, I really hope you can get this, because with this we can do a lot of things, and without that it would be difficult. Okay, so that's your first goal for.
This has rings. This limit. Is this limit as rings?
Is this
Sorry?
limit as rings?
Yeah, it's limited like the category of rings.
Yeah, it's a limit in the category of rings. Yeah, thank you. Correct. So it's the inverse limit. Let me write it down. In the category of rings. Thank you. So what you, after you kind of get used to it, you can see that, so here's another exercise. That's also in your worksheet. You can show that ZP is a Hausdorff, compact, totally disconnected. So these are all topological features, right? Hausdorff, compact, topological, totally disconnected. But now algebraically, it's a local ring. So it has a unique maximal ideal, and here it is. And what else? Yeah, let's see how elements look like. So you can show in this, think about it as a completion, or in any way, in any of the three ways you'll see that you can think about it like that. You can see that ZP consists of elements of the form A0 plus A1P plus A2P square, etc. But now you're taking an infinite sequence. You allow this infinite sum, and these AIs they are in 0, 1 up to P minus 1. So you can think about the P-adic integers as this formal power series in P. And why does this converge? Well, we know that P to the n, so what's the norm of P to the n? The norm of P to the n is P to the minus n. And that goes to 0 when n goes to infinity. So that is to say, these are all Cauchy sequences. And if you think about it in this, here, you can just see how the coefficients, how you can build the coefficients, and just when you go from an plus 1 to an, you just truncate your power series. Okay, that was a quick review of the P-adic integers, but I will need a few more things here. Not before I will ask you if you have questions.
Is it possible to define the integers using that representation and defining addition and multiplication as you use?
Yeah, you could. Except that we always want them to be the same object. So you need to make sure that all the properties are there when you define it.
Sorry, we just
Okay, now
the questions that are happening in the room in Hawaii. So if you could repeat the question and then the answer.
yeah, sure.
Thank you.
So the question was whether you can define the P-adic integers in this way and define their addition. So I think you can do this, but I'm also saying you should be careful to include all the properties because we want it to be a topological object. Yeah, it's not only when we define the ring operation, this is not the end of the story. Yeah, so you as long as you make sure that this is a topological object, and yeah, so you can see how it's totally disconnected. It's like a Cantor set, right? You start with a0, then you start with 0, you have p choices out of to choose a0, then you have p choices for your next approximation. So that looks like a tree, okay? And it becomes a totally disconnected, compact topological space. And now what we have done, well, we have embedded Z inside Z2, and then Z3, and then Z5. And each of them now is local. There's only one prime ideal, PZP, in each one of them. So algebraically, it's a simpler object. But also it's a compact topological space, group, ring, so you can do harmonic analysis on it. And that was Tate's quite amazing theorem, which I want to talk a little bit about now. So, sorry? 5 minutes? 5 minutes, okay. So we have a Haar measure on ZP or QP when we think about it additively. So this is a locally compact group, QP, with respect to addition. So we have a Haar measure. So we have a measure such that for every measurable set, you have that the measure of the set is the same when you translate. That's the analog of the Lebesgue measure. If you haven't seen a topological harmonic analysis on locally compact groups, which I will talk a little bit about. And we also have a measure on QP with respect to multiplication, and I will denote this measure by mu star. So that's going to be the measure of a set. When I translate it multiplicatively, that's going to be the same measure. And now what Tate did in 1951 in his PhD thesis, he looked at the Riemann zeta function, and now I will put gamma over S2, pi to the minus S2, and the infinite product. And he interpreted each one of these Euler factors as an object in harmonic analysis and wrote it down as a P-adic integral, which we're going to use a lot. So one of your exercises is to show that you can write down this 1 minus p to the minus s as an integral over zp, or should I probably should say qp without 0, of the function x p to the s, the indicating function of zp, and with respect to the multiplicative measure on zp or qp. I thought I'll solve this exercise for you, but maybe I don't have enough time, but we can talk about it later on today. And the other factor is equal to the integral over r star of x to the s, now the usual absolute value, and now e to the minus pi x squared, and then the Haar measure, the multiplicative Haar measure on the reals. Now what you can see here is the following. This is a character, a multiplicative character, and this function here plays a similar role in the harmonic analysis over QP and over the real numbers. I will say more about that, but what I wanted to emphasize is that you have here two different words. You have the real numbers. So if we're looking now at Q, we have the real numbers, then we have Q2, Q3, and so on for all these completions. And by the way, a theorem of Ostrovsky says that these are all the possible completions of the rational numbers. So this is the collection of all the completions of the rational numbers. And what Tate did, he related all the factors in the completed Riemann zeta function. He related them to harmonic analysis over these locally compact fields. Now, as I said, we don't have such a rich structure where we go, but we can still have interpretation. We will still have Euler product decomposition. That's one of the things we're going to talk about in representation zeta functions. We can still write down the local factors as P-adic integrals. They will not be as nice as this integral. So you'll see this is a particularly if you see this for the first time, this must be overwhelming, but don't worry. After 5 minutes, you'll see that this is something very easy written. Yeah, this is very easy and very natural after you kind of if you think about it after you've seen it. So we are going to have P-adic integrals, and but they will call Igusa zeta functions, and they will be related to model theory, and it will be less kind of symmetric from harmonic analysis point of view, but we will see how helpful these parts are. So my message to you, and I'm done for today, is to revise the P-adic numbers and ask me or your demonstrators any question until you feel comfortable with them. Okay, thanks.
Okay, thank you, Uli. Any questions for Uli? Either from here or from Hawaii.
What is the symbol in the middle of the first integration?
Sorry, the audio there is quite muffled. If you can get closer to the mic, it will probably help. I think there's a big mic in the middle somewhere.
The question was about the first integral, about the symbol in the middle of the integration.
The indicating function of the p-adic integers.
Yes.
Yes.
So one of the things that I said that ZP is a ring is, so I do have 4 or 5 minutes for the questions, or should I, how brief? Okay, all right. So if you look at ZP, so ZP is going to be the subset of elements in QP with norm less or equal to 1. And by this property, the multiplicativity, this is closed under multiplication. By this property, and here you see why you need the ultra one, the ultrametric. It's closed under addition, so this is a ring. And so what we are taking here is the indicating function of the p-adic integers inside QP. I mean, you can think QP cross is just QP without 0. It doesn't matter. You can just drop 0 has measure 0. So there's no issue here. And this is the indicating function of the p-adic integers. Now, at the same time, this function has a role in harmonic analysis. It's the fixed points of the additive Fourier transform on QP. Okay, I don't want to get into this too much at this point, but I can't even. But I'm happy to talk with anybody of you, any of you who wants. So this is the indicating function of ZP. Now, in the real number for the real absolute value, this is not an ultra norm. This is just a norm. So if you try to define the ring of integers, it's not closed anymore. It's just the norm can, you add numbers and the norm can be arbitrarily large if you add them. So you can think about this as the analog of the missing integers for the real numbers. We can't define the integers, but there's this function that plays a role which is exactly the role that this indicating function is playing in the harmonic analysis over QP. And so that's function, if you know a little bit of harmonic analysis of the real numbers, this is a fixed point under the Fourier transform over the reals, over the additives. So these are the analogs. That's kind of the amazing insight of Tate and Vail and all the people who were around Tate at that time. More questions? Question in the chat.
I can say it out loud. It's just, is a ring uniquely determined by its Dedekind zeta function?
No. Yeah, that's a very natural question. I think the answer is no. Yeah, those of you who are quick can Google this. This is a very good question. It should be no, but I don't know how. It should be no. It can't be true.
Okay, thank you.
Sorry?
Have we said which of these
I said maybe briefly. I didn't write it down. So so the Dedekind zeta function is the generating function of the BNR from the beginning of the talk. BNs, this is the number of ideals of index n in the ring of integers. Okay, this is the number of ideals in R of index n.
This should give a product formula.
And there is a product formula. I will post my notes on Slack as well, which are more organized than what I did here. I prefer to talk with you. You're here, and we can talk and we can ask questions that can be less formal. But my notes will be more formal and with the label definition, the label theorem, and so I'll put them on Slack later on. More questions?
Nothing here.
Sorry?
Nothing here.
Let's thank Uri again.